Okay, we are still here, chapter 14. So we're getting into sort of the back half here of chapter 14, and last time we got into really titrations. So again, titrations obviously are used when you have typically a solution of unknown concentration or something like that, and you have a known solution. We talked about really a specific type of titration, which was a strong acid and a strong base titration. And again, in this titration, pretty much up in the burette here, we had our base and we were adding it really to our acid here. So that was the titration sort of setup. We saw what's referred to as a titration curve. And again, typically that's pH on the Y. That's the volume of, if you're adding base, for example. If you're adding acid, it could be that as well. And we typically will get this sort of S-type shape for a titration curve. Maybe the equivalence point is somewhere there. And remember that we do typically titrate to the equivalence point, which in an acid-base titration, the moles of the acid will equal the moles of the base at that point. And there's really kind of four parts to a titration curve that we talked about. And sort of the first part of it is really before you begin. So kind of that's the first part there. Before you add, in this case, any base to your titration, that is what you're going to start with. And to figure out the pH at the beginning here, because all you have is a strong acid, you pretty much could go right into your pH equation and figure that out, since that strong acid would provide you with the H plus concentration that you have. So you don't have to worry about anything like that. You haven't added anything at that point. So you basically just have a strong acid sitting there in the beaker. So you get the H plus concentration, go right into that pH equation. Once you first start your titration and work your way up towards the equivalence point, and that's sort of the second part of the titration curve, and that is before the equivalence point. Whatever you are adding at that point, you're going to have less moles than what you started with. And that's obviously because at the equivalence point, they're equal. So before that, whatever you're adding, you'll have less than. So this will require, as we talked about, an ice table, and definitely during a titration, you are definitely adding volume. So that's going to be a moles ice table that you're going to do. Because at this point in the titration, pretty much your acid in this example would be the excess reagent. You will basically use the ice table to figure out the concentration of your acid after you add your base. At the end of that first ice table, as we talked about, after you do it in moles, you should convert it back to molarity using the total volume that you added. At that point, you will then still have a strong acid left over. And again, from that, you could get the H plus concentration, and then you could go right into the pH equation like we did before. Now, as we also talked about, and why, again, people often say, I just added one drop and, my indicator went super dark pink. We saw, as we talked about last time, that as you approach the equivalence point, you typically will see a very quick rise in the pH, and it will kind of go vertical. And again, because the pH is rising vertical, that means that you're not adding a lot of volume to do that. So very little volume will actually change the pH a lot. Again, that is why your indicator, like phenolphthalein, for example, could be colorless and then go like super dark pink when you add just like one drop there as you approach the equivalence point, because although you didn't add a lot of volume, the pH changes a lot even with that little bit of volume. And because the indicator works again on a pH range, your pH range has changed a lot, and the color that you would see would also change a lot. Um, when we do reach the equivalence point in this type of titration, we know that the moles of the acid will equal the moles of the base. And if you write out your equation and all that, pretty much you will only be left really with a salt that will not go through hydrolysis. You basically will have a neutral salt. And the pH in this type of titration should be 7 at the equivalence point. Obviously, all the acid that you started with gets used up. All the base that you added gets used up. You're left basically with water and a neutral salt. So we would expect the pH to be 7 in this particular type of titration. The last part of the titration curve is after the equivalence point. So maybe your indicator did change and that did not stop you. So you just kept adding. We also typically see, in addition to kind of going vertical to the equivalence point, once you are at the equivalence point, you typically will continue that vertical pattern past the equivalence point, and you oftentimes will see a pretty good jump in pH as you're kind of going through there. That's why sometimes it's hard to kind of get a point there at the equivalence point because it rises so quickly and stuff like that. But you typically will have this second jump after the equivalence point in pH. When we do this, this is obviously after the equivalence point. That again is going to require an ice table. Also, obviously, needs to be done in moles. And what's going to happen at this point, once you go past the equivalence point, we're going to get a change that's going to occur. So instead of our acid being the excess reagent and our base that we're adding the limiting, it actually switches. And our acid actually is the limiting reagent. We don't have enough of it, and we have way too much base because all you're doing is adding more base at this point, right? You're just dropping it in from the burette. So the ice table here is actually to figure out the concentration of your strong base. Again, you would do that ice table of moles. At the end of it, convert it back to molarity using the total volume that you added up until that point. That will again get you not the H plus concentration, but the OH minus concentration, which will allow you to get to the POH and finally to the pH at that point. So we have 4 sort of distinct parts on the titration curve. A lot of times when you're doing titration problems, as I might have mentioned last time, it's a really good idea to sort of have an understanding of where you are in the titration curve. And you oftentimes can kind of know the calculation you should be doing before you even try to do the calculation. So that obviously helps with the calculation if you sort of know what you're supposed to be doing. Any questions on any of that there that we talked about? So again, what we talked about last time, what we just went over here, is specific to that type of titration, strong acid and strong base. Now let's talk then about a different type of titration, which is going to be a titration of something, a weak acid and a strong base. So we'll take something like acetic acid here, which is a weak acid. And we're going to react it there basically with our strong base, which is our sodium hydroxide. So once again, sort of the orientation of what's happening up in the burette here is going to be our sodium hydroxide. And down in the beaker is going to be our acetic acid. So again, here we are adding base to acid. And we will get a titration curve, as you can see, also sort of a similar sort of S value or structure here that's happening with this titration curve. So just like the previous titration, there really are 4 important parts to this titration curve as well. So let's take a look at each of them like we did previously. We'll start with step number 1 there, which is basically right there at the beginning. So if we start at step 1, which is before we add sodium hydroxide, the only thing that we have here in the beaker is our acid. And in this case, we only have basically a weak acid. Once again, here we have not added any base to it or anything like that. We haven't really started the titration, basically just got our beaker of weak acid. So if I need the pH of a weak acid, this is something we've done before. This is a Ka problem, yeah? Which means you need an ice table. This can be done in molarity because, again, you haven't added any base to it, so you can do it in molarity. You're going to do your ice table. You're going to solve for X. X in that ice table will equal the H plus concentration. And then you could go into your pH equation. So you can see here a little bit different than the previous titration that we talked about, where we had a strong acid to begin with, where all you have to do basically is go into the pH equation. Here, because we're starting with a weak acid, you basically got to do a weak acid problem to figure out the pH. Again, you have to do that ice table, and you can do it in molarity. You can make an assumption if it works, or do the quadratic, whatever it may be. But that will be how we will get our pH here to open up. Any questions on that there? All right, then let's talk about what happens when we actually do start the titration. So once we actually start adding base, just like previously here from the first drop, basically to right before the equivalence point there, that's going to be really the second part of the titration. So in this case, we are going to be at the second stop there, and that is before the equivalence point. So when we do that, we're obviously going to get a reaction. So here we're going to add some sodium hydroxide. We're adding to our acetic acid, which is what we're starting with. And this is going to give us a double displacement reaction, which is going to make some sodium acetate on our double switch there, and our OH and H from the acid going to make a little bit of water action, yeah? So at this point, we do need to do an ice table. And again, here we are adding volume, which means we do need to do this ice table in moles. So we do have to do it in moles. So if we do an ice table here, and much like what we talked about in the previous titration curve, I'm just going to make up these numbers. So I'm going to say that I started with 4 moles of my acid, right? So because I'm before the equivalence point, should the moles of the base, which I'm adding, be less than, equal to, or greater than 4? It should be less, right? Because I'm before the equivalence point. So again, I will go with my friend 2 here. And we're going to have 0 on this side. Now, at this point, the change here, as we talked about last time, typically if you do it in moles, you will have a number for the change, not really an X or anything like that. And we're going to go with, really at this point, it's the sodium hydroxide, which is the less number of moles there, and that's the limiting reagent. So the change here is going to be our moles of sodium hydroxide that we added in this case. That means when we reach equilibrium, we will have none of the sodium hydroxide. In my example here, we'll have 2 moles of this guy. We'll also have 2 moles of this guy. First off, any question on that so far? As we talked about before, as soon as you do really this first ice table, just put it back to molarity. You'll put you in pretty much the right units that you need for any type of calculation you're going to do. Here we will divide by the liters, which again would be our total volume at this point. That would be obviously how much sodium hydroxide we added and how much acid we started with. That's going to give me molarity here. We'll also convert this guy into molarity divided by the total moles as well. At this point, if you're not sure what's going on in terms of what you have happening at this point, again, you can use your ice table to help you. You can look at your ice table, and pretty much at the equilibrium line, you have this guy, which is sodium acetate left. You have this guy, which is acetic acid. Are these two things related to each other? These two things are related to each other. That is a weak acid, right? And is conjugate base. That is better known as a buffer, right? So you actually just made a buffer in this case. That's what I was talking about when we were talking about buffers earlier. A buffer cannot be made out of a strong acid or strong base. You can't say I have a strong acid or strong base, I want it to be a buffer. But you could react, for example, a strong base with a weak acid, and the end result of that reaction is you actually made a buffer. So you could actually make a buffer from a reaction of a strong base with a weak acid. The buffer is not involving this. The buffer is actually involving what was left over at the end of the reaction. So that is how you can make a buffer, also known as part 3 of the experiment that we're currently doing, is to make a buffer just like that, basically, where you react a strong acid or strong base with one of the components. Now, because it is a buffer, you have really 2 options as to how you could get to the pH. Probably the easiest would be to correctly now use this equation, which is our Henderson-Hasselbalch equation. You could go right into it at this point. Or if you wanted to, you could do a second ice table and not the Henderson-Hasselbalch if you choose to do that. The second ice table would be based off of the weak acid and it'd be a Ka. The key, right, if you chose the sort of second ice table approach, as we've talked about a number of times when we're doing buffers, you want to make sure that when you get to your second ice table, if you choose that route, you should have a molarity here, 0, and most important, you should have a molarity on that side. Otherwise, if you didn't do that, you didn't do the buffer calculation. Again, you did the weak acid calculation. So again, probably less room for error if you just go into the Henderson-Hasselbalch, since this is actually the appropriate place to use it. But again, if you choose to do the ice table, you can do the ice table as well. Any questions on that there? So different than the last titration here, anywhere from like the first drop to before the equivalence point, you're going to make a buffer pretty much. And this type of titration is going to be the end result of that reaction that's going to happen as you're making your way towards the equivalence point. That is also why when we look at it, by the way, a couple of differences that we see. The starting pH for this guy, since it's a weak acid, is a little bit probably higher than the starting pH for our strong acid. And we have a little bit more buffering action sort of happening here, not as strict of a sort of change in pH that's happening. We have a lot of buffer, right? And when you reach right here and you go big jump to your equivalence point, this is because essentially what you just did is you broke right through your buffer that you made, right? So you made this nice little buffer as you're doing your titration. And then towards the end, as you get to the equivalence point, you broke through your buffer because you added too much base at that point. And that's why you see that big jump in pH to the equivalence point, because you have buffering activity and then you broke it basically. And you see that big jump because it cannot buffer the sodium hydroxide that you keep adding at that point. Any questions on that there? So speaking of that, because we've now broken through our buffer and we headed a big jump here-ish in pH, we're going to land on our equivalence point in this case. And that, again, is the third important part of this titration curve. So at the third part, we're at the equivalence point. We obviously are going to need a reaction of sodium hydroxide again. And again, that is what we're adding, plus our acetic acid, which is what we're starting with in our beaker. And we will end up with our sodium acetate. No minus. Sodium acetate here and our water. Once again, we definitely need to do this ice table in moles. So again, I'm going to start with my 4 moles of my acetic acid, which means I'm at the equivalence point. So how many moles of sodium hydroxide should I have? Should have the exact same number, because that's basically what the equivalence point means. I should have 4 moles at this point. I believe we talked about it last time, but just to remind you, in certain problems that you might come across, they may not tell you the volume to reach the equivalence point. So sometimes you do need to calculate that. So there are a couple different ways you could do that. Since you know what the moles should be of your sodium hydroxide, and you most likely will have the molarity of your sodium hydroxide, you could just simply use the molarity equation and figure out the volume you would need to get there. You could also, if it's a one-to-one relationship, which it probably will be in most cases, between the acid and base, you could actually use M1 V1 equals M2 V2 and The 1s are the acid, the 2s are the bases, however you want to do it. And you can use that as well to figure it out. Lastly, if it is a one-to-one relationship and they both have the same concentration, the acid and base, you need the exact same volume to reach the equivalence point as you started with in terms of acid. So sometimes you do need to figure out, how much volume to get there. At this point, we have 0 here to start with. We can't pick the wrong number. I hope that's going to be 4 all the way across here. That means, like we anticipate, all of the sodium hydroxide we added is gone. All the acetic acid we added is gone. And that leaves us here 4 moles, which of course we're going to convert back to molarity, again using the total volume here. That would be, again, how much sodium hydroxide you added, how much acid you started with. Any questions on that table? So if we look at this ice table, we could see what we are left with. And at this point here, that is all we are left with, basically. That is, I believe, a salt, they call that here in the business, right? So what type of salt is that? Should I worry about that salt? Is the pH going to be 7? The answer is no, it's not going to be 7. And you should definitely worry about this salt. It should give you sleepless nights. Yes, this salt is going to break apart. It's going to break apart into a sodium ion and our friend, the acetate ion. We know the sodium we don't have to worry about, but our friend here, the acetate, came from this guy, which is acetic acid, which is a weak acid. That means that salt's going to go through hydrolysis, right? Because it comes from a weak acid. So what's going to happen is this salt that was generated in this reaction will then continue to react and go through a hydrolysis reaction with water. And since it came from a weak acid, this would be the conjugate base, which means it's going to act as a base and going to actually accept the H+. And when it accepts the H+, it will make acetic acid where it came from, and it will make hydroxide. So unlike the last titration curve, where at the equivalence point all you had was a neutral salt where the pH would be 7, just based on that reaction, the pH should be acidic, basic, or neutral. Should be basic. So we will have a basic pH here in our titration because of the salt going through hydrolysis. This will be a second ice table. So good news, bad news is you need to lay up a second ice table when you're at the equivalence point. The equilibrium concentration of your salt will become your initial concentration here. So this guy is going to come over here, basically, right? The rest of the table will be a normal table. And since we're doing molarity here, we're going to go back to our x's, yeah? We'll have our initial minus x, we'll have x and x. We're going to solve this by using our k, right? And we're going to solve for x. By the way, what k do I need? K, A, B, C, D, F, G. Should be a k, B as well, yeah? You most likely will not have the KB in this problem, so this will be another one where you have to use that KW equals KA times KB to convert it. So you're going to have to do that as well, so you don't use the incorrect K value. Any questions on that there? By the way, when I solve for x, what does x equal in this case? X equals the hydroxide concentration. So when you solve for x, that is the hydroxide concentration, which means you got to go POH first and then pH, yeah? So you can see it a lot different than the previous titration where essentially you got a pH of 7 because you have a neutral salt. Here at the equivalence point in this type of titration will require basically 2 ice tables. The purpose of the first ice table is actually to figure out the concentration of your salt. The second ice table is really how you get to your pH, which is a hydrolysis problem to figure out what the pH will be based on that salt. It will always be a basic situation in this case because you're starting with a weak acid. And that will always produce a conjugate base that will go through hydrolysis and always produce basically a basic pH at the equivalence point. Any questions on that there? And that is what we see if we look here. Our pH at the equivalence point is, that looks like 8 point something, I think. So 8.72 versus a pH of 7. So as you can see, it is basic in this case. Any questions there on the equivalence point? All right, so last part of this titration curve, again, it didn't stop you the whole indicator thing. You're going to go past the equivalence point. So we're going to continue on here now past the equivalence point. Once again, we're still going to get our equation, a little sodium hydroxide here, which is we're adding, plus our acetic acid, what we started with. Still producing our sodium acetate and our water here. So once again, we will need to do an ice table at this part of the titration. I will start with my 4 moles of acetic acid. But now, like we've seen before, we are past the equivalence point, which means the moles of acid and base are no longer equal to each other. That means the moles of sodium hydroxide should actually be now more than what I started with, right? Because we are past the equivalence point. So whatever we're adding, we get to the equivalence point, they're equal. And if we keep adding, now they're more, basically. So we'll make up a number here of 6 and 0. What happens, much like we saw in the last titration curve, is there's a switch that occurs. The sodium hydroxide in this example is now like your excess reagent because you just keep adding it. You got plenty. You just keep dropping it in from your burette, basically. The acetic acid becomes your limiting reagent at this point. So here, again, you want to pick the correct number. As I mentioned a couple times before, go with the small number, even though your head may tell you not to. Yes, so go with the small number here. The acetic acid is now our limiting reagent, and we're going to actually use up all the acetic acid in this case, and that is going to be the change. That'll give us 2 moles of this guy, nothing of this guy, and 4 moles of this guy. Once again, we're going to convert back into molarity here using our total volume. How much we added and how much we started with, obviously here, total volume. So again, at this point, when we analyze what we got left over and blank the screen, and undo the screen there, we got a little sodium acetate and a little sodium hydroxide. Are these guys a buffer? They are not a buffer. Yeah, they're definitely not a buffer. They're not even really that much related to each other other than they both have a sodium in it, right? Other than that, they're not related to each other. So not a buffer. Again, common error, 2 numbers into the Henderson-Hasselbalch equation because, well, I need 2 numbers to do that, and that would be incorrect in this case. So you do not want to use it here. So what do we have? We clearly have, as we saw in the previous step in this titration, we have a salt that will go through hydrolysis. And as we saw at the equivalence point, that salt will go through hydrolysis and produce hydroxide because it's really a base, right? It's a conjugate base, right? And will produce hydroxide. We also have this guy here, which is sodium hydroxide. That is definitely a base. That is what type of base? That is a strong base, right? So what we actually have at this point in the titration is 2 bases. We have basically the salt that will go through hydrolysis and act as a base, and we have a really strong base, which is sodium hydroxide. Between the two, which one should be the stronger base? It is the sodium hydroxide, right? It doesn't need to go find anybody. It just needs to go in. It's going to break apart and produce hydroxide. The acetate's got to go find the water, do a little reaction, and produce a little bit of hydroxide. So the major contributor to the pH at this point is actually going to be this guy here. It's going to be the strong base. Even though the acetate will still continue to go through hydrolysis, again, all that strong base has to do is go for a swim. It's going to produce hydroxide right away. So what we do at this point in the titration is, because the sodium hydroxide is going to be the major contributor, we actually ignore any contribution from the salt, because what it's going to produce is going to be very minimal compared to what sodium hydroxide is going to produce in this case. With that being said, because this is a strong base, that pretty much will give you your hydroxide concentration, which means that will get you to the POH and ultimately to the pH at that point. So as you go past the equivalence point in this type of titration, you have to do one ice table in moles. The purpose actually of this ice table is very much like it was in the last titration, is to really figure out what is the concentration of your strong base. And once you figure out the concentration of your strong base, you will then have the hydroxide concentration, and then you could get to the POH and then to the pH. Any questions on that there? So this titration, a little bit different than what we saw with the previous titration. There are 4 different parts, but the good news is you've done all those calculations previously. The hard thing for people is to realize what calculation you should be doing. So this is where I was talking about earlier. If you understand where you are in the titration curve, especially like a titration curve like this, you should know what type of problem you're doing before you even actually do the problem. So for example, if I was doing this calculation here and this titration, I know before I even start the titration, I have a Ka weak acid problem, because that's all I have. I know that once I start the titration, before I get to the equivalence point, I have me a buffer problem that's going to happen. I know once I reach the equivalence point and this type of titration, I have a hydrolysis problem. And lastly, I know basically once I go past the equivalence point, I have a strong base. So if you know where you are in the titration, you actually know what type of calculation you should be doing, and that should obviously help you with the calculation, rather than what a lot of people sometimes do, which is they just jump right into it, right? They just jump into it with the numbers and start calculating. And then at some point they don't know what they're doing because they don't know where they're at. So again, this is one of those times where maybe getting directions is a good thing. Yes, so you don't get lost. Yeah, and you know what you should be doing before you even do it. So again, first step there requires 1 ice table with molarity. Second step, minimum 1 ice table, could be 2. Third step, definitely 2 ice tables. And last step there, 1 ice table. So these are the things you want to think about. Any questions on any of that there? Oh, so let's try one just for fun here. I don't know if it's fun or not, but we'll try. Let's do this titration. So let's say we want to know what is the pH after. We'll do that. After 23 milliliters of 0.1 molar acetic acid. I'm sorry, sodium hydroxide. Let me get that right there. Sodium hydroxide there. Of sodium hydroxide is added. There we go. To 25 milliliters of 0.1 molar acetic acid. Ka for acetic acid, 1.8 times 10 to the minus 5. All right, give it a go. I'll do it as well. See what we end up with. And it's the one we've been talking about. So we have sodium hydroxide up in the burettes. And again, we're adding it to our acid here. So obviously we do need a reaction. We do need to do an ice table. We obviously need to do it in moles since we're adding. So we'll start with that. So if we want our moles of sodium hydroxide, again, we'll convert our volume into liters, and we'll times it by the molarity here of the sodium hydroxide, which is 0.1 moles per liter. Liters will cancel. Going to get us there 0.0023 moles of sodium hydroxide. We'll do the same thing for our acetic acid. Moles of acetic acid here We'll take our volume, convert it to liters, divide by 1,000, or move the decimal point over. 0.025, also 0.1 moles per liter. Liters will cancel. Gonna get us here, looks like 0.0025 moles. All right, so now we can write our reaction here for our ice table. We're going to do our sodium hydroxide here, which is what we're adding, plus our acetic acid, which is what we started with. Going to give us our sodium acetate. Remember how to write that. There you go. And our water in this case. We're going to use our moles. So initially here we have 0.0023 moles of this guy. We have 0.0025 moles of this guy. Am I before, am I at, or am I after the equivalence point at this point? How would I know if I'm before or at the equivalence point or after it? So if I'm at the equivalence point, the moles should be same. If I'm before the equivalence points, the moles of what I'm adding should be less than or more than? Should be less than, right? In this case, the moles of what I'm adding is less than what I'm starting with. So this is less than this, which means I am before the equivalence point at this point in the titration, yeah? Any questions on how you determine that? So again, the ice table can help you determine where you are at the in the titration curve if you're not sure. And again, just by simply labeling what things are, looking at the comparison of the moles, it will help you determine that. All right, 0, because I'm before the equivalence point, that means whatever I'm adding is going to be the limiting reagent, minus 0.0023 minus 0.0023 plus 0.00230. When we get to the equivalence or the equilibrium here, we have none of that guy. We'll have 0.0025 minus 0.0023, 0.0002 moles. We'll have 0.0023 moles. At this point, we want to convert back to molarity here. So our total volume at this point, we started with 25 milliliters of the acid. We added 23 milliliters there of the base. That looks like a 48 milliliter grand total. So we're going to divide each of these, converting that to liters, 0.048 liters on each of those guys there. We'll go 0.0002 divided by 0.048. Gonna get us here 0.00417. 0.0023 divided by 0.048. Gonna get us there 0.0479 molar. Any questions first off on the ice table here? All right, so again, if you're not sure at this point what you have going on, which by the way, you should be knowing where you are in the titration, we could look at the ice table and it will help us hopefully. We have sodium acetate and we have acetic acid still left over. These two guys, are they related? They are a buffer, which what I was talking about earlier, you should have known you should have ended up there because you're before the equivalence point in this type of titration, which means you're always going to end up at a buffer. So again, these are the things you want to think about as you're doing these problems to help reinforce that you're perhaps doing it correctly. Again, at this point, you do have two options. You can ice table it up again if you wanted to. I personally can go with the Henderson-Hasselbalch because it is a buffer and might as well do that. To use the Henderson-Hasselbalch equation, the pH is equal to the pKa plus the log of the base over the acid. Obviously, here we will need our pKa value, which is minus the log 1.8 times 10 to the minus 5. Going to give us a 4.74 as our pKa. So that's going to give us 4.74 plus the log. Again, we want to go with the base on top. Which one's the base? It is the sodium acetate, right? The other one's acetic acid, which obviously would be our acid. So we're going to go with the 0.0479. If I didn't lose a zero there, and we're going to divide that by 0.00417. So let's see what we end up with there. Divided by 0.00417. Going to do a little log of that. We're going to add that to 4.74. That's going to roughly give us, at this point in the titration, a pH of 5.80. Yeah. Which obviously is before the equivalence point, because we know at the equivalence point it should be basic, right? So here we are a little bit before the equivalence point. Question on that there. We can even see how we did since this was this titration. So 23 is right there, past 5.6, before 6, 5.8 fits right in there. So that's pretty good. Not bad. Question, yeah. What's that? Uh, you'll need to know how to solve all steps. You'll technically need to know how to solve anywhere along the way on the titration curve. I would say there will probably be problems, homework problems, maybe other problems where you might have to do multiple stops along the way. But to answer your question, when you're focusing on whichever place you are in that titration curve, you don't have to do all 4 calculations to do that. You just need to identify where you're at and do the proper calculation for where you are calculating for on your curve. But with that being said, you will be asked at some point along the way to probably figure out, the pH anywhere along the curve, and you should be able to do that, basically. Yeah. Also, I think we talked about it last time, but just so, again, there's no misunderstanding. When you do come across a problem, either on the test, quiz, or in the book, and there's like a titration curve that you're doing, and they ask you the pH at multiple stops along the way, typically you don't continue on with the volume, if that makes sense. So they say, hey, what's the pH after 5 milliliters, and what's the pH after 15, and what's the pH after 25? You usually think of all those problems as individual problems, like you started at 0, you opened up to 5. What's the pH? You started at 0, you opened it up to 10. You started at 0 and you open up to 25. So usually, very rarely, we come across a problem where they're like continue on with the volume from each step. So you want to think of them as just kind of individual. You're starting to very begin of titration. And if it was question A was what's the pH after 5, you just open up the 5, get the pH. And the next one was what's the pH after 20 milliliters? You're starting at 0, you open up to 20, you get it. So usually you don't kind of continue on with the volume and those type of problems where you have multiple steps along the way. Other questions? All right. Funness. There we go. Well, that's 2 types of titration curves, so might as well do 3. Why not? So let's talk about a titration curve now that's different as well a little bit. This is a strong acid with a weak base. So the setup here in this titration is a little bit different. Actually, up in the burette in this case is going to be the acid, the HCl. So we're actually adding acid to base, and down in the beaker flask is going to be our base, and in this case, NH3. So this is our weak base and strong acid. So in this case, we actually see the same titration curve, except it's upside down. And that is because what we're starting with in this case is not an acid, but it's actually a base. And we're adding acid to base, which means the pH actually should start high because it's a base. And as you add the acid, the pH is coming down. So that's why we see the titration curve here. We start at a higher pH and we end at a lower pH. That's opposite of what we saw before, where we had an acid we started with and we're adding base to it. So with the acid, we're going to start at a low pH. And as we add the base, our pH starts to increase, right? So we get up there to the very high pH. So it's kind of the upside down version of the titration curve that we just talked about. So let's talk about the same 4 sort of parts in this titration curve. So we'll start with here, which is our normal before we add any acid in this case, and actually start the titration. So before we do any of that, once again, in our beaker here, we have pretty much just ammonia, which is a weak base. So how do we get the pH of a weak base? This is going to be a KB problem. It's basically a weak base problem. And to remind you how you do that, hopefully you still remember, that is an ice table, surprisingly enough. This can be done in molarity because you have not added volume at this point, so you're all good to go. You're going to obviously solve for X in your ice table. Remember that because this is a base, you will then, X will equal the hydroxide concentration, not the H plus concentration. And that will get you to the POH and then to the pH. So this is very similar to the previous titration we just talked about, but in that one we had a weak acid, so you're doing a Ka problem, and you will get the H plus. Here you're actually starting with a weak base, so you're still going to do the same type of calculation, except when you get that X, it will be the hydroxide, and thus you will get the POH and then the pH. That is because your weak base, for example, like ammonia, will basically take the hydrogen there from the water, and you will produce hydroxide in that reaction, right? So this is basically your weak base reaction that you're going to get. In this case, I'm going to take that H plus, make a little NH4 plus, OH minus, right? So that's basically, what's going on in that case. Any questions on that one there? Now we're ready to start this titration. Again, we're starting with a pretty high pH. And much like the other titrations from the first drop all the way down to our equivalence point, basically, is going to be the second part. That's going to be before the equivalence point in this titration. And if we take a look at that here, before equivalence point. We obviously are going to get a reaction, so we're going to have our hydrochloric acid that's going to react, that we're adding in this case, to our ammonia. The hydrochloric acid is going to send an H plus over, and that is going to give you NH4 plus and Cl minus. I am going to kind of keep them separated. If you want to keep them together as ammonium chloride, you can, but I'm just going to kind of keep them separated, and you'll probably see why in a second. But for now, I'm just going to keep that side separate. At this point, we're going to do an ice table here. It does need to be in moles since we are adding, obviously, volume. So once again, with my made-up numbers, I'm going to start with our classic 4 moles here for our base. Because we are, again, before the equivalence point, the moles of the HCl should be less than that 4. So we'll go with the 2 like we've done before. And we will have 0. Change here going to be -2, -2, and +2 moles. That means at equilibrium here, we will have 0. We'll have a couple moles this guy, couple moles this guy. By the way, for the Cl minus, why am I not writing anything there? Cl minus is a neutral salt. So again, perhaps don't put any numbers there if you don't need to, so you don't use it. So obviously, if you kept together, you would just have one number anyways on the other side, ammonium chloride. We're going to convert back to liters here using our total volume like we've done before. And again, if you're not sure what's going on at this point, we can use our ice table here to help us. At this point, we have ammonia and ammonium. These two guys are definitely related to each other. That's going to be a weak base and is conjugate acid, also better known as a buffer. So just like the last titration we did there or talked about, before the equivalence point in this type of titration, you're going to hit a buffer, just like you did before. The difference here is you're going to hit a basic buffer most likely for most of it. The other one, you're going to hit more of an acidic buffer along the way. But here you'll hit more of a basic buffer because, again, we're starting high in terms of our pH. That, again, gives you the two options of you can Henderson-Hasselbalch it up, which is probably the preferred one, or you could also ice table. Again, you could use NH4 plus in the Ka value. You could use NH3 in the Kb value. And you could do either one, basically, whichever way you want to go. Remember, though, that at this type of titration here, you probably will have a Kb value given to you because of ammonia. So again, if you're going to use the Henderson-Hasselbalch, you want to make sure, again, that you get to pKa. And you want to make sure you put the base on top and the acid on the bottom. You could, again, in this case, also use the POH version of that equation with the pKb, and then subtract 14 to get to the pH if you want to do that. Or again, you could go right into the Henderson-Hasselbalch, but just make sure you have those numbers sort of available to you. That's also your double option there on the ice table. You could do a Ka ice table with the NH4 plus, or you could do a Kb ice table with the NH3. So it's just your option as to how you want to do it. So very similar to the last titration, you're going to always hit a buffer here. This is the other example of part 3 of the experiment we're doing. This is, we just made a buffer from a reaction of a strong acid with a weak base. So again, you can create a buffer in vitro, which means in the test tube or in the beaker, by reacting a strong acid with a weak base. The buffer, once again, is what you get at the end. It does not involve the HCl other than it was used to make the buffer. So this is how, again, you could kind of make a buffer from a strong acid and weak base. Just like we saw, we could make a buffer from a weak acid and a strong base as well. So this is another way you can kind of produce a buffer. Any questions on that there? All right, so that brings us here down to our equivalence point. We also see what we saw before on our titration curves, which is we see actually in this case a drop in pH to the equivalence point. And that is because, again, we're adding HCl, and what we just did at that point is that nice buffer we made in that region, we just blew through it by adding more HCl. So we blew right through the buffer. So now instead of a small sort of change in pH, we're going to see that big change in pH with a little bit of volume. And that's why we're going to see actually the drop down here in pH to the equivalence point because we blew through the buffer that we made. So step number 3 here is our equivalence point step. And at this point here, we are going to have our reaction, which in this case is our HCl plus our ammonia, making our NH4 plus. And again, either you can keep it together or break it apart, your choice. And initially here, if we start with our 4 moles of NH3, because we're at the equivalence point, those moles should be the same. So we will have 4 moles of this guy and 0 of this guy. Change is going to occur here. Again, can't hopefully pick the wrong number here since there's only one number to pick. I would choose that number then. That's going to give me here 0, 0, which is what we should expect there on the left-hand side because we're at the equivalence point. We will have 4 moles of this guy, which once again, we can convert back to molarity. Really what we have left at this point, if you kept it together, is ammonium chloride, which is a salt. And that salt will break apart, obviously, into chloride, which we've already established is not going to do anything. But in this case, we do have ammonium, which came from this weak base, which means it came from a weak base, going to be a relatively strong conjugate acid. And much like we saw in the previous titration, that part of the salt will continue to react with water and we will get a second reaction that's going to occur, which is our hydrolysis reaction. So we will get our NH4 plus part in this case, reacting with water. And again, it's going to react as an acid, which means it's going to donate the H plus over there since it came from a weak base. When it does so, it will always create where it came from, which is NH3. And in this case, we will produce H3O plus. So the pH at the equivalence point here should be acidic, basic, or neutral. Should be acidic because of this salt going through hydrolysis. So different than the previous titration where we expect it to be basic at the equivalence point. In this titration, we expect it to be acidic, and different than the first titration we talked about the other day, where it will actually be neutral at the equivalence point. So these are different things that's going to happen. We will do an ice table here using our equilibrium value. From here, we're going to bring it over to our initial, and now we can do a normal sort of ice table with X's and molarities. The K value I need for this, A, B, C, K, A, right? So I will need a Ka. As I mentioned before, probably if you're doing this problem, once again, you will have probably the Kb value given to you for NH3. So you can again use the Kw is that Ka times Kb to flip it around. When you do this one, the good news is, I guess, is you're going to solve for X. And in this particular case, X will actually equal the H plus concentration, which means you could go right into the pH in this case. So once again, this one is very similar to the previous titration. At the equivalence point, you will need two ice tables. Really, the first ice table is to figure out what is the concentration of your salt that you should have. The second ice table is a hydrolysis ice table, and that salt will always produce H3O plus because it comes from a weak base, which means it will always be an acid. It will always donate the H plus to the water, and you will always generate H3O plus. And again, you need to make sure that you get to the Ka value and solve for the pH. Question on that there. All right, so that is the third part there. Once again, we're going to see a jump past the equivalence point as well. It's actually jumping down, I guess, and in terms of pH. And our fourth spot here is after the equivalence point in this case. So once again here on step 4 there, which is after the equivalence point, we will have our same reaction we've been looking at. So we are adding this guy. We are starting with this guy. Again, starting with my 4 moles of NH3. Once again, here we are past the equivalence point, which means we should have more moles of whatever we're adding, which in this case is the HCl. So making up that number of 6. Sounds like a good number. Here, we're going to get a switch. It will now be the base that's the limiting reagent, as it's the smaller number. So it will get used up. That means at equilibrium here, we'll have 2 moles of this guy, nothing of this guy, and 4 moles of this guy. Once again here, divided by our total volume, converting everybody back into molarity. We can now analyze our ice table to see what's going on. Once again, we're still not going to be concerned about the chloride because it is a neutral salt. At this point, we have NH4 plus and we have HCl. Hopefully, you know that is not a buffer, even though you have 2 numbers here. So we have NH4 plus, which is definitely a conjugate acid, and we'll go through hydrolysis as we saw. But we also have HCl, which is a strong acid. Out of the 2 here, it's going to be that strong acid. It's going to be really the major contributor of H plus in this solution, because again, all it has to do is go in to break apart. again, the ammonium has got to go find some water, do a little reaction. So much like we did in the previous one, at this point in the titration, we're really going to ignore the contribution here of the NH4 plus, because this guy here is going to be our major contributor to the H plus in that solution. And because it is a strong acid, that will give you the H plus concentration, which means right on into the pH equation, and you could calculate your pH at that point. So at this point in titration, you're pretty much just dumping a bunch of acid in there past the equivalence point. You're going to get a big buildup of H plus, which is why we see that big drop in pH or jump in pH after the equivalence point, because you basically have nothing to handle any of that H plus coming in, and now you're just adding H plus basically at that point, and you're going to get this big jump. You need to do one ice table basically to figure out the concentration of the strong acid you have left over, and then into the pH. Any questions on that one there? All right, then let us try one here. Let's go with what is the pH after you, oh, let's see. After you add 27 milliliters of 0.1 molar HCl to 25 milliliters of 0.1 molar ammonia. Kb for ammonia, 5.6 times 10 to the minus 10. Go with that number. Sounds like a good number. Why not? Good. Okay, so let's take a look since we're getting to the end here. Obviously, we're going to get our reaction here that's going to happen, our HCl, which we're adding, plus our ammonia here, which is what we're starting with, and our ammonium chloride, basically. We obviously need to do this in moles, so we'll take 0.027 times 0.1 for our HCl, and that will get us 0.0027 moles. We'll do our 0.025 times our 0.1 for our NH3 to get 0.0025 moles and 0, right? Am I before, am I at the equivalence point, or am I after the equivalence point? I am after, right? I have more moles that I'm adding than what I started with, so I am definitely after the equivalence point, which should tell you what you should end up with. So let's see. That means that this guy is going to actually be our limiting reagent here, and that's going to be the change 0.0025, 0.0025 plus 0.0025 moles. That's going to give me here 0.0027 minus 0.0025, 0.0002 moles, 0 there, 0.0025 moles. We can go total volume at this point, 27 we added, plus 25 we started with in terms of the volume. Gonna get us 52 milliliters. So we'll divide this guy by 0.052 liters. We'll divide this guy by 0.52 liters. That's going to get us there 0.0002 divided by 0.052, 0.003846, and 0.00250 divided by 0.052. Going to get us 0.04808. Here we have, not going to worry about that. We got ammonium and we have HCl. And because we know we're after the equivalence point, we're pretty much just dumping in the HCl at this point, right? And although the NH4 plus will go through hydrolysis, this is the point of the titration. We're going to ignore that because this is a strong acid, which means that, frankly, that is my H plus concentration. And I could go right into the pH at this point. And that is going to get me here pH of about 2.41, which is definitely acidic because we're just dumping in base at this point. Let's see how we did. So we were at 27, which is between those two numbers. So 2.4 looks like it's between those two numbers. So that's pretty good. Question on that one there.